Howdy ho, my little hostess cupcakes. Today we're going to go over all of Chapter 8, hopefully. If I run out of time, I will continue with the Chapter 8 review tomorrow. Many of you asked me to go over 8.3 in depth. Some of you even asked if we could just redo 8.3. If you look at the study guide, which we're going to, that's what I'm doing the review on today. I'm just going to go over the entire study guide. If you look at the study guide for 8.3, this is the smallest section, right? This is not that much. So it's not as in-depth and crazy as the detail in the book, because we can get really easily bogged down in those details. So we're basically just covering VSEPR theory in 8.3, which we'll get to after we cover 8.1 and 8.2. I have a feeling that we might have to do a day 2 of review, because I'm also going to have some more questions for you to do at the end of all of this. Anyway, we'll get to there when we get there. Okay, so 8.1, molecular compounds, aka covalent compounds. So we're going to look at covalent bonds. What are they? Well, we know that covalent bonds, as opposed to ionic bonds, are bonds in which the electrons are shared rather than accepted or donated. So here we have ionic bonding. We have the sodium ion donating one of its electrons to chlorine. So when this happens, we have sodium getting a full-on plus and chlorine getting a full-on minus. So a really easy way to remember the difference between ionic and covalent is that ionic compounds are going to have, there's no partial positive or partial negative about it. They're going to be fully positive or fully negative, the ions in the compound. Whereas with covalent compounds, when we're looking at polarity of compounds, we can have partial positives and partial negatives, or completely neutral, no partial positive or no partial negative in a non-covalent, or excuse me, a non-polar bond or compound. So we have ionic bonds. These are where electrons are, one is giving up an electron and the other ion is accepting the electron, as opposed to covalent bonds where we have the electrons being shared. You see the electrons being shared here in this bond between the two hydrogens. Okay, so we got that. Let's talk a little bit more about some of the differences between ionic and covalent. So we have donate or accept electrons, as opposed to sharing electrons. The shape of these two different types of compounds. Remember that ions take on what's called a crystalline. Wow, I totally have a problem with that. Oh my. Crystalline shape, which means when they break up into their ions, we have, I'm not actually gonna, I'll do this. Okay, we have a plus ion right next to a negative ion, and then we have a plus ion on the other side of that. So these all line up in imagine this is like a box, a cube. All right, here's my cube. We have a negative down here, a positive, a negative, positive, negative, etc. So these line up in this crystalline shape in a three-dimensional crystal structure, like in a cubic structure. You can think about salt, right? Salt is kind of crystalline. It's little pieces, little crystally looking things, little cubish shapes, right? Those are all just NaCl, plus minus, all lined up in this three-dimensional crystalline structure, as opposed to covalent compounds, which exist as, we're going to call them discrete molecular units. Discrete molecular units, meaning we don't have these two high. That's kind of a hard one. Let's say we have CH4 as an example. We don't have carbon and the 4 hydrogens breaking up into individual ions like we do here in an ionic compound, right? They remain CH4 and they interact with other CH4s that are all in this compound as well, or in this substance, however much substance we have, right? So these are discrete molecular units, whereas this is a crystalline structure. All right, so that's good for the differences. Let's do one more. So, yeah, because I forgot I asked you for 3. So another big difference are the physical properties of these two different compounds. So ionic compounds, these are also called inorganic. This is also called inorganic compound. That's spelled wrong. Organic. And anything that is covalent are called organic compounds. So inorganic and organic. All right, so inorganic compounds or ionic compounds, they have really high melting and boiling points. It takes a lot to break them down, basically. So we have high melting and boiling points. Melting, MP, melting point, and boiling points, as opposed to organic compounds, which have low melting points and boiling points. All right, and the fourth one I'm going to give you is this thing called charge separation. There's a difference here in charge separation between ionic and covalent compounds. So charge separation is like how much how positive an ion is, or a side of a molecule is, and how negative a side of an ion or a side of a molecule is. So basically, it's when I was saying earlier that ionic compounds are like only 100%, they're not going to be partially positive or partially negative, right? They're either going to be 100%, the ion is going to be 100% positive if it gives up an electron, or it's going to be 100% negative if it accepts an electron, right? So the charge separation for ionic compounds is extreme, meaning we only have 100% positive or negative ions, and it's not so extreme, with covalent compounds. Even in polar covalent compounds, we have partial negative and partial positives, right? Okay, so that's the charge separation, we call this. So those are the 4 big differences between ionic and covalent compounds that you need to know. Well, if you know 3 of them, you're good. And you're going to need to be able to identify ionic and covalent compounds. So I'm going to give you a list, like I've been doing, of different compounds, like you got on some of the homework questions. You're gonna have a list of different compounds, and you're gonna need to know which ones are ionic and which ones are covalent. Which I'm not gonna go over right now because I feel like you all do all right with that. So if you do need work on that, you know that, and you should get on that. All right, now let's move on to some definitions. You need to know the definition of a molecule and a diatomic molecule. I'm not going to give you the definition because they're in the book. Just the book definition is perfect. Remember, a molecule is a neutral group of atoms joined together by covalent bonds, and a diatomic molecule is a molecule that contains 2 atoms. So if something has 3 atoms, it's not a diatomic molecule. And sometimes people get confused that only these Br2, Cl2, etc., O2, N2, that these are the diatomic molecules. That is not the case. These are diatomic molecules. However, this is also a diatomic molecule. This is a diatomic molecule. This is a diatomic molecule, right? So a diatomic molecule is just something with 2 atoms. All right. So we got that. A lot of you did not answer this question on your Chapter 8 questions, so we're going to spend some time going over that because I feel like you didn't understand it. we are going to use ammonia as our example, NH3. All right, so ammonia, this is the name of the molecule. This is the molecular formula. And then we have a couple other, I think that's what it says. What is it? What information does it give us? So the molecular formula tells us obviously the atoms and the number of atoms, the type of atoms and the number of atoms in a molecule. And I say that you need to be able to write the molecular formula if I give you the structural formula and or the space-filling molecular model. So if I give you NH3 like this, if I give you the molecular formula and I ask you to provide the structural formula is this. It's not a Lewis structure or a dot diagram. You don't have to draw the electrons. This would be the structural formula. The space-filling model would be something like this. I would give you a picture, and then you could fill in what each atom is, like that. All right, so this is the structural, and this is the space-filling. All right, you need to be able to write the molecular formula from any of those, and vice versa. You need to be able to write the structural and space-filling given the molecular. You will need to do that on the quiz, so you be sure you understand how to do that and the difference between all of them. Alrighty, that's it for 8.2, or 8.1, sorry. Now let's go on to 8.2. Alright, so the octet rule. What is it? The octet rule states that atoms tend to form compounds in ways that allow them to achieve the electron configuration of a noble gas. So, aka, usually, well, we're going to say 8, this means 8 electrons. So all of the atoms except hydrogen want to have 8 electrons around them. Remember, hydrogen wants to have 2, which is the noble gas, the helium configuration, right? Helium has 2 valence electrons. So hydrogen wants to form to get the helium noble gas configuration, whereas every other atom that we're going to talk about in this class wants to have 8 electrons, which is what all of the rest of the noble gases other than helium have. So what that means, I'm going to kind of talk about this in terms of ionic bonding and covalent bonding, just for a refresher. So we're going to talk about it in ionic compounds first, then we're going to talk about it in covalent. Okay, we're going to talk about ionic first. Okay, so let's look at sodium. So all of the atoms, when they're forming compounds, they want to have 8 electrons around them except for hydrogen. So let's look at the electron configuration for sodium. Yes, remember this? 1s2, 2s2, through 2p6, 3s2. So sodium has 11 protons and 11 electrons in its neutral form. When sodium is going to form an ionic compound, it wants to achieve a noble gas configuration, aka it wants to get 8 electrons around it. That means that we need 8 electrons in the outermost energy level. Remember the energy levels here. Let's look at that. We have our first energy level, so this is energy level number 1. We have our second energy level with 8 electrons in it, right? Because we have 2 in the S and 6 in the P. And then we have our third energy level out here. So in the outermost energy level, we want to have 8 electrons. So what we can do to get 8 electrons is we could either add 7 electrons into this outer energy level, 2, 3, 4, 5, 6, 7. We could add 7, right? That would achieve the noble gas configuration, or we could just take one away. And in chemistry, although you might not see it right now, we want to do things as easy as possible, right? So, or as simply as possible. So what we're going to do is we're going to take away that that last electron in the outermost energy level. Whoops, this is wrong. Sorry, this should have been 3s1, not 2. But anyway, I'm erasing it now. So we get rid of this one. And now in our outermost energy level here, we have 8 electrons, right? We have 8 electrons out there. All right, so this has achieved the noble gas configuration. But remember, we have 11 protons in sodium, and we have 11 electrons. But if we take away an electron, if we take one of these away, maybe, there we go. Now we have 10 electrons. So therefore, the overall charge on this atom is going to be +1, right? Because we have 11 pluses and 10 minuses. So now we have a +1 charge on the on the atom, right? So this is how. And then, of course, I mean, where did that electron go? We gave that electron to chlorine, or let's say, is that, yeah, well, we're going to say we gave it to fluorine because that has less electrons. All right, here we have fluorine, right? And fluorine has 7 electrons in its outermost energy level, right? In the 2 energy level, it has 2 plus 5, which is 7 out here. So it wants to achieve 8, just like every other atom. So what it does is it accepts that electron from sodium. Sodium gave that electron down here to fluorine. When that happens, of course, our fluorine atom goes from 9 protons and 9 electrons to having 10 electrons. Therefore, it has an overall -1 charge on it. And these two form an electrostatic interaction between that negative charge and that, because of that negative charge and that positive charge, they form an electrostatic interaction between them. This is very different than covalent bonding. If we look at covalent bonding, in covalent bonding, we still want all of our atoms to have 8, unless you're hydrogen, electrons around them. But we're not going to be giving one away and accepting any, or 2 or 3, however many electrons we're dealing with. We're not going to be getting rid of or accepting any electrons. We're going to be sharing them. So let's look at methane, classic example, CH4. So what we do first is we have these 4 valence electrons around carbon, and then we have, I'm going to draw this in a different color. We have our hydrogens, 4 of our hydrogens here, and they all have 1 electron each. So what we do is we look at each individual atom in order to determine how many electrons are being shared around each of those atoms. So here, for example, we have 2 electrons around hydrogen. Remember, hydrogen wants to get the noble gas configuration as helium. It wants to have 2 electrons, so that hydrogen is good. Same with this hydrogen. It has 2. Same with this hydrogen. Same with this hydrogen. All right, so let's look at our carbon and make sure that one has the proper number. It's fulfilled its octet rule. So we have 2, 4, 6, 8 electrons being shared around the carbon. So everything follows the octet rule in this case. So we're not having any. We're not getting rid of any electrons. We're not adding any electrons. Let's look at one more example here. Let's look at carbon dioxide, CO2. All right, so we have carbon again here in red, and it has 4 valence electrons. And then we have, let's use different color. Let's use purple for oxygen. We have oxygen, which has 1, 2, 3, 4, 5, and we'll put this over there, 6. And we have another oxygen that has 1, 2, 3, 4, 5, and 6. Okay, so what we're going to do here is we're going to share. They're going to have these 2 electrons be a pair, these 2 electrons be a pair. All right, so is that enough? If we look at this oxygen, it only has 2, 4, 6, 7 electrons around it. This one, too, only has 7 around it. And the carbon only has 6 around it. So we need to do something else. Carbon needs to somehow gain 2 more electrons. So what we're going to do is we're going to share another here. This carbon, or these ones, we're going to move them so that we form another bond here. And we're going to take this last electron of carbons and this last electron of oxygens, and we're going to form another bond there, like that. Now if we count all of the electrons around each oxygen, we have 2, 4, 6, 8. And if we count all the electrons around the carbon, we have 4 on one side and 4 on the other side, so we have 8 there as well. So the octet rule is fulfilled here also. Okay, So that's the difference here in the how the octet rule plays a role in covalent and ionic bonding. Some exceptions to the rule. We already know hydrogen, but there's also boron. That's a big exception. And sometimes phosphorus. Boron is the main one that you need to know that is an exception to the rule. Boron, B. All right. And obviously, definitely hydrogen as well. All right. Single, double, triple covalent bonds know how many electrons are shared in each. For example, one pair of electrons are shared in a single bond. So here, where did we have? Here we have a single bond, right? Because one pair of electrons, we have a pair of electrons there. But here we have two pairs of electrons being shared. Therefore, we have a double bond. If I were to draw this out, it would look like this, right? So two pairs of electrons is a double bond. And of course, three pairs of shared pairs of electrons is a triple bond. All right? Okay. So electron dot diagrams or Lewis diagrams, you need to know how to draw electron dot structures given a molecule. And you need to know what unshared pairs or lone pairs are and why they're important. They're going to be important when we start talking about VSEPR theory. I put the R and the P the wrong way, but there we go. And they're also going to be important in determining polarity or non-polarity of molecules, covalent molecules as well. I'm not going to go over how to draw electron dot structures given a molecule, but you are going to need to be able to do that. So if I give you BF3 and ask you to draw me an electron dot diagram of that, or electron dot structure, whatever, then you need to be able to draw that. If you don't know how to do that, you need to contact me. Right. Okay, so you need to know both of those. Coordinate covalent bonds. You need to know what a coordinate covalent bond is and how they form. So let's look at the classic example, which is carbon monoxide. So let's draw a Lewis structure of carbon monoxide. We have carbon with 4 valence electrons around it, and we have oxygen with 1, 2, 3, 4, 5, 6 around it. So somehow we need to get an octet around both carbon and oxygen. So we're going to share this one and this one and this one and this one, right? Because they're the lone pairs. There's some lone pairs. That makes it pretty easy. We have 1, 2 there now. Whoops. I'll keep sticking with the right colors like that. And then oxygen, we're going to have like this. And we have 1, 2, 3, 4. All right, but if we look at this, around carbon, we only have 2, 4, 6 electrons, and oxygen is good. It has 8. So what in the heck are we supposed to do? Well, a coordinate covalent bond is where one atom donates a pair of electrons. Rather than just a single electron, it donates an entire pair in order to help the other atom achieve the octet rule. So what happens is this pair of electrons there goes, and it's shared now between carbon and oxygen. So now we have these two down here, and then those shared pairs between them, right? So now around carbon, we have 2, 4, 6, 8, and we already had 8 around oxygen. We still have 8. So this is what's called a coordinate covalent bond. It's where one atom of a molecule shares, it donates both electrons rather than them each donating one. It donates both electrons to a bond. That's how they form. All right, bond dissociation energy. No one answered this question, or if you did, I guess there were a couple people that did, but most of you did not answer this question on the homework, which is a bummer, and you got in incomplete because on not answering questions is in not asking me any questions to help you answer your own questions is just ridiculous. So if you do that, just FYI going forward, sorry, little side note here because I just remembered. If you do that going forward, you're getting 50% or a 0 on your assignments. You can't just answer the question like 5 out of 10 questions or 2 out of 10 questions because those are the only ones you know. You need to ask me clarifying questions and try your best to answer them. You're not going to leave homework blank. So a lot of you got 50% for doing incomplete homework, and you will continue to do that if you continue to get that grade if you continue to leave answers blank without asking me questions. Okay, so bond dissociation energy. What is it? So bond dissociation energy is one way that we can measure the strength of a chemical bond. It is the amount of energy that's required to break a bond between two atoms that have a covalent bond. All right, so let me pull up, really quickly, also the units that we talk about bond dissociation energy in is kilojoules per mole, which you're going to understand what a mole is a little later on. So for example, if we look at, I'm going to pull up this table. Okay, so they're often given to us in a table like this one here, the bond dissociation energies are. So if we look at this table, we have this bond, and then we have a value next to it. We have this bond and a value next to it. So this tells us that it takes 436 kilojoules per mole to break a hydrogen-hydrogen bond. So the higher the value next to these bond types, the stronger the bond. So you look here at a hydrogen-oxygen bond. It takes a lot more energy to break a hydrogen-oxygen bond than it does to break an oxygen-oxygen bond, right? Okay, so that's what they tell us. That's what the bond dissociation energies tell us. And of course you should know that when bonds break, that requires energy. We have to put in energy. We have to put in this amount of energy. For example, if we want to break a hydrogen-hydrogen bond, we have to put in that amount of energy. So breaking bonds requires energy. And when these bonds form, this energy is released, right? So we're going to learn a lot more about that in the future, but you need to know that. How are bond dissociation energies and bond length related? This is in your book in a table on page, I don't know what page, but here it is. So if we look at bond dissociation energy and bond length, the more energy that is required to break a bond, like this hydrogen bond, the shorter the bond length. So a way you can think about this is that it's a lot easier to break a bond that has a long bond length, right? If this is the bond length, that bond is going to be easier to break than a bond that has a very short bond length, right? I can't think of a good metaphor right now, but hopefully maybe you can think of a metaphor. Share it with me if you can. So it's easier to break this longer bond than it is to break this shorter bond. Or another way of thinking about it is that in this shorter bond, they're really holding on super tight to each other with a lot of energy, right? So if you're holding on to something with a lot of energy, you're going to be holding it really close to you. But if you're just kind of holding something kind of loosely, not with too much energy, it will be farther away from you like this. So there's lots of different ways that you can kind of make your mind remember this. So bond dissociation energy, higher bond dissociation energy means shorter bond length. So they have an inverse relationship. Be able to explain the relationship. I just said that one. Okay, given a table it's page 236. There it is. Okay, given this table that I just shared with you down here, this one, be able to determine which type of bond is stronger. For example, if we were given the information on this table, which bond is stronger? The bond between the hydrogens in H2 or the bond between the carbon and the hydrogen in the atoms of CH4. So let's look at that. Which bonds, or which molecule would, the question, I'm not going to say which one has a higher bond dissociation energy, right? Like I'm going to say if the bonds between, how much energy would it take to break this, if you have one molecule of H2 and one molecule of CH4, which one is going to require more energy to break the bonds, all the bonds between all of the atoms? If I wanted to turn them all into ions, which one would require more energy? Think about that for a second. So to break that bond, or to break all of these bonds. Which one is going to require more energy? Well, this bond has a bond association energy of 435 kilojoules per mole. And this one, we have a carbon-hydrogen bond, which is 393 kilojoules per mole, but we're breaking 4 of those, right? So we actually have 1,572 kilojoules per mole total. So while the hydrogen-hydrogen bond is stronger, it's going to take more energy to break up all of those carbon-hydrogen bonds, right, in methane. If I said which is going to require more energy, just a CH bond or an HH bond, that one is easier, right? We know that this bond here is 393 kilojoules per mole, so that's simple. We don't have to multiply it or do anything like that. We know that this one is going to require more energy because the hydrogen-hydrogen bond is stronger. Okay, so that's what you need to know about bond association energy. Also, the homework question from the question 8 problem, or the chapter 8 questions, that was a good one. In number 5, I think it's letter C or D. That question was a very nice question about bond association energy. So if you don't know how to do that, or if you struggled with that, you should look at the key, and you should, you should look at the key or watch my video. I think we'll maybe go over that homework tomorrow. So look at the key or wait for my homework, me going over it tomorrow. Okay, so that's it for 8.2. Okay, moving on to 8.3, bond theory. So VSEPR theory. What is the VSEPR theory? The VSEPR theory is used in order to describe or explain how molecules exist in three-dimensional space because of their electrons. So there's all of the different molecular shapes that we've learned. Those are all associated with the VSEPR theory. So this theory states that the electrons, the electron pairs in a molecule, they cause the shape of the molecule to adjust so that the electrons pairs stay as far away from each other as possible. So electrons don't want to be around other electrons. Electrons and electrons repel. Electrons and protons attract, but electrons and electrons repel each other. Negatives and negatives, they don't like each other. They don't want to be around one another. So let's look at the very basic example again of methane. So in methane, we have this carbon surrounded by 4 hydrogens. So each of those bonds, there's 2 electrons in each of those bonds. So the VSEPR theory tells us that these electrons are pushing away from each other. All of them are pushing away from each other. None of them want to be by each other. They want to be as far apart as possible from each other. So actually, right now, the angle between them is only 90 degrees, right? These are all 90-degree angles between each pair of electrons, right? These electrons are 90 degrees away from each other. Well, if we orient ourselves or this molecule just in 2D space like this, that's as far away from each other as they can get. But molecules they don't exist in 2D space. They exist in 3D space. So the shape that this molecule takes, we have the carbon in the middle. We're going to have a hydrogen like this. So now we've increased this angle to 190 degree, or 109 point, I think it's 0.9 or something. 0.5, 109.5. And now we have what's called a wedge and a dash. So we're going to draw this tetrahedral shape with a wedge and dashes. So the wedge indicates that this molecule, this hydrogen atom is coming out at you. It's pointing out of the board at you. This hydrogen atom is pointing into the board. Okay, so these three right here, they're all in the same plane. They're all on a sheet of paper. Okay, they're all on one flat sheet of paper. But this one is going back behind the sheet of paper, and this one is coming out in front of the sheet of paper. So when the molecule organizes itself like this in space, now those electrons, because these are all electrons here, right? There's electrons in all of those, right? So now these electrons can all be even further apart from each other. They're all of these angles are 109.5, every single one. So rather than existing in 2D space, they exist in 3D space. And the VSEPR theory says that the electrons are going to push themselves away from each other as far as they possibly can without breaking the bonds. Okay? So that's how we get this tetrahedral shape. Let's look at another molecular shape. So let's just look very simply at a linear shape. All right, so let's look at carbon dioxide. All right, so why is it linear? Well, in each of these, we have 2 electrons here in each of these bonds, right? So these ones, obviously, in the 2 bonds, they're pretty close to each other, right? But there's no other way we can have them. So what we have is this group of electrons wanting to push away from this group of electrons as much as possible. So another way of thinking about this is, if we didn't have the VSEPR theory, or if we did, why aren't the electrons like this? Why isn't it in a 90-degree angle like that? Well, because like this is a 90-degree angle between those sets of electrons. But here, if we have it in a linear shape, we have a 180-degree angle, right? So the VSEPR theory says we want to increase that angle as much as we possibly can. Those electrons repel each other as much as they possibly can. There's no other way. The reason that these ones have to be so close to each other is because carbon and oxygen on each side, they're each sharing 2 pairs of electrons. There's no other way. You can't, it's impossible to have, I don't even know, we can't do something like this, right? Like, they have to be right by each other. We can't have them all stretched out. So that's unfortunately the closest. They have to be close to each other in that double bond. But okay, so this is 180 degrees. Let's look at our bent shape. Our bent shape, remember, is actually, we'll get water. Our bent shape is like this, and we always draw those 2 electrons at the top like that. Well, this is how we normally draw water. But water is actually, so we have molecular shape, right? The shape here is bent, but we also have the molecular geometry, right? So the molecular geometry of this is not bent, it's actually also tetrahedral. Right? And we have the electrons out here. So the electrons are actually pushed further out in oxygen, or in water like this. So here, let's draw them all like this. So here, the electrons want to be as far away from each other as possible, so they take the tetrahedral shape to push away from each other as much as possible, to increase that angle between all of the electrons as much as possible. So that's how we get this bent shape, because we still have these 2 other lone pairs that we're dealing with. So that's why water can't look like this. Whoopsies. Sorry. Okay. Like this, because the angles between all of the electrons would be 90 degrees, right? This would all be 90 degrees. Everybody would be 90 degrees away from each other. Well, the best and most efficient, or the farthest away we can get them is, what about like this? What if we did, I don't even know. There's no other way to do it, actually. There's no other way to do it. So that's the farthest, the best way to increase the bond angle as much as possible is to put this molecule in a tetrahedral shape, to put the electrons in a tetrahedral shape or geometry. Okay, so that's what you need to know about VSEPR theory. What is it? How does it dictate where electrons will be in space? Linear, bent, trigonal planar, pyramidal, and tetrahedral are the shapes that you're going to be responsible for. You're going to be responsible for being able to draw them like I just did right now, and you're responsible for being able to identify which shape it is. And if I give you the shape, you need to tell me the name, and vice versa. Oh, yes, and if I give you the molecular formula, or the structural formula, or the space-filling model, like I was telling you about earlier, you'll need to, if I give you the molecular shape, you'll need to be able to give me the molecular formula, or the structural formula, or the space-filling model. And I give you an example down here. What is the molecular shape of CH4, which we already know is tetrahedral because I just did it, or draw the molecular shape given this structural formula. So if I give you this structural formula and say, we'll say Cl, and I say, what is the molecular shape of this, or what is the molecular geometry of this, you need to know that it's tetrahedral, all right? Or if I give you a trigonal planar, or something like, what is it? I think it's like this. If I give you the dot diagram or the structural formula like this, you need to be able to tell me that's trigonal planar, for example. Okay. Let's see how much time we have left. All right, so we're actually going to stop there. And most of you, I don't think I'm actually going to go over 8.4 unless any of you, if you want me to go over 8.4, you need to ask me very specific questions in the comment on today's assignment. But otherwise, I'm going to move on tomorrow. Well, we're moving on tomorrow either way. I'll give you a brief review, or I'll tell you where we can go over, where you can find stuff for 8.4. But since we just did that and there's videos all uploaded from me, I'm not going to spend a lot of time going over 8.4. So if you have any specific questions or any specific thing you'd like me to go over from 8.4, please leave a comment and I'll go over it tomorrow. But you need to leave it like right now before the end of class. And also, I will be going over some homework problems tomorrow. So if there were any homework problems from the assignment that was due today, the assignment that was due on Friday, the Chapter 8 questions, the overall review of Chapter 8, if you have any specific questions on that homework assignment, then you need to ask me also today in a comment. Tell me which one you want me to go over. That's your assignment for today, is to tell me what parts, if any, of section 8.4 you're having some struggles with, and you need to ask a specific question. Don't just say, what's molecular polarity? Ask a specific question, please. And also tell me if there are any questions about the assignment from Thursday, the Chapter 8 questions, overall review questions from Thursday. That needs to be done right now before the end of class. And that is it. Otherwise, your homework assignment for tonight is to read 9.1 and take notes, and those are due tomorrow before the start of class. Let me know your questions on Google Classroom, just in a comment, private comment, or a public comment, whatever you prefer. If I don't get any comments, I assume that means you are all good and I don't need to go over anything, and you're all going to ace the 8.4 part of the quiz on Friday. All right, that is it. Thank you. Goodbye.